In our last lecture, we talked about the factors that affect the overall temperature of the Earth. And so that equation was the sigma, the Stefan-Boltzmann constant, multiplied by the Earth's actual temperature to the fourth power. This was multiplied by a term that involved the albedo, the solar constant, and the ratio of 4, and then the term that we had for global warming. So I'll label these. So we can see from this equation that the factors that are going to affect the actual temperature of the Earth are mainly these three right over here: albedo, solar constant, and the gases that affect global warming. So let's take a minute and talk about each of these three different effects and also reflect on what is and has been happening with our climate. So the first step that I want to do is to look at global average temperatures over time. So we're going to go over to the climate.gov website, which has a lot of really useful information regarding climate change. So let's just go ahead and switch right over there. All right, so this one is looking at the global average temperature over time. And the graph that you're looking at the top up here is looking at the overall trend in both warming and cooling from the time period of 1901 to 2017. So each of these areas we are looking at how much warming we have. So the amount of change that we have, this light tan, this is a 0.1 degree increase, and that's contrasted by this light grayish blue, and that's minus 0.1 degrees. So these two sort of balance each other out. The slightly orangey one is plus 0.2 degrees, and then the darker orange is plus 0.3 degrees. So you can see that over a time period of this 1901 to 2017, we have modest change. This would indicate that there's a certain amount of fluctuation going on with the few overall increases, and generally more warming than there is cooling. If we change our temperature, or excuse me, our time scale though, and we look instead from just the past 30 or so years, 35 years, excuse me, we can see a much more dramatic change taking place. We have a little bit more cooling in some areas, like right down here at the south end of South America, but we have more areas that are seeing really dramatic increases. So you can see from the scale here that these dark red, this is plus 0.5 degrees. So plus 0.5 degrees doesn't necessarily sound like a whole lot, but it's the trend that is potentially concerning. So if we look at our trends in the global average temperature, and of course we talked already about how for the places that we don't have measurements, like before, I don't know how long people have been actually taking careful temperature measurements, probably since at least the mid 1800s. But from before that, we can use proxy data, which I'll talk about a little bit later. And if we look at our overall trend, this surface average temperature, which we do have information from 1850 on, not for every single place, but we have enough different locations, that they set up this graph looking at this 30-year time period, 1981 to 2010, and said, let's just average the temperature over this time period. We'll call that our 0 point, and then we'll be able to track what the changes in the temperature are relative to that 0 point. So you can see that down here, pre 1900, we had pretty stable temperatures. There's a little bit of fluctuation, but you don't see any trend lines. But as you are passing 1900, and we see a much bigger increase in the amount of global industrialization, you can see this overall warming trend, a little bit of a stable trend right here, and then another much more significant warming trend since about, I don't know, 1980, I guess. So this increase is what we're kind of concerned about, that we don't want to keep increasing the temperature indefinitely because this is not a stable thing for our climate. So coming back to our point here, we're seeing a global increase in the change in temperature of our planet, and this is a trend that we are going to try and understand by thinking about the equation that we had over here. So we identified these three different factors, the albedo, the solar constant, and global warming, to think about. So let's take a look at each one of them. So if we think about the solar constant, this is how much energy is coming from the sun. So this doesn't change a lot. I mean, eventually I guess the sun will burn out, but that's on such a long time scale, we don't need to worry about it. We do see that we have about an 11-year cycle for sunspots, and the sunspots will increase the solar radiation, but again, we're having like maybe a 2% change even in this 11-year cycle, and of course there's not really anything we can do about it either way. So the solar constant, we just have to deal with whatever we get what we get. So most people don't really spend a whole lot of time worrying too much about the solar constant since we can't do anything about it. However, we do pay attention to the albedo and to the gases that are present in our atmosphere. So if we think about the albedo, we've already talked about some of the materials that are going to change the reflectivity of the atmosphere. And so this is the surfaces that reflect and how much that overall reflection happens. Let's take a look at this diagram. It gives us a general sense for the percent reflectivity of these different materials. So you can see that the things that are the most reflective are the clouds. So different kinds of clouds have different reflectivity. And then snow is even more reflective depending on how fresh it is. And then some areas where we have very pale sand are going to be really reflective as well. And then the things that are much less reflective are usually darker soils, forests, and water, which kind of surprises me. I would think water would reflect more, but apparently not. And then depending on how wet the materials are, then those are going to decrease the albedo too. So remember that increased albedo means generally cooling because we have more light is reflected back into space. And if we have decreased albedo, then this is going to be less cooling, I suppose. Not actually warming, but less cooling as we have less light reflected. So we can see that land use, like turning land into crop lands, is going to change the albedo of certain spaces. So if we use agriculture, this is going to increase it, but it's actually going to be less cooling than if we have forests. It's going to reflect more than the forests do. So I suppose some of the transfer of forest into cropland is going to have a net cooling effect. However, if we think about this fresh snow issue and the ice issue, these are some of our more reflective materials. And so as we warm up the environment and more snow melts and ice packs melt and glaciers melt and turn into water, which is not very reflective, we're going to have a net effect that is called a positive feedback loop. So in this case, the positive feedback loop is going to involve warmer temperatures are going to melt the snow and ice, and so we reflect less, doing less cooling by reducing the albedo, and so increase the temperature more, and melt more ice. The average global albedo is, as we said, about 30%. But we do need to pay attention to changes to the Earth's albedo based on changing land coverage and land use, because it can have a pretty significant effect on either warming or cooling. We'll get back to albedo more in a little bit as we talk about some of the strategies that have been proposed. So when we think about our third factor here, which is greenhouse gases, let's talk a little bit about the main greenhouse gases that we are looking at, and then the two main factors that we are paying attention to. So these are the main gases based on either abundance and or warming potential, which we'll talk about in just a moment. All right, so global warming potential, or GWP, this is a term that was proposed to talk about the two factors that affect how much a greenhouse gas is going to actually do warming. And so this is a combination of first, how well the gas is going to absorb IR and how much of the spectrum it absorbs. And then two, its lifetime in the atmosphere. And most of the global warming potential papers that you will see, they will track it over 100 years. So this is like how much potential for warming over 100 years. All right, so let's just quickly go through some of our major gases. So carbon dioxide is listed as having a global warming potential of 1. It is our reference. Everybody else is compared to the carbon dioxide. Now, carbon dioxide has a long lifetime in the atmosphere. Once it is released, it stays in the atmosphere for a pretty long time. These are years, not months or anything else. But it must not be super effective at absorbing infrared radiation, and we saw that it only has 2 vibrational modes that absorb infrared. And several of the other gases are much more effective at absorbing infrared radiation. So methane, CH4, depending on where you look, this has a global warming potential of about 28 to 36. And so it has a short lifetime in the atmosphere comparatively. It's only about 10 years. But it is pretty effective at absorbing IR. So nitrous oxide, N2O, this one has a much more significant global warming potential. It's somewhere in the 265 to 298 range. I got these numbers off of the EPA website. Its lifetime is not totally well understood, but it's probably more than 100 years. It absorbs IR well, obviously even better. Well, much better than carbon dioxide. It's hard to know how to compare it to the CH4, but there's actually a formula for it. Now, all of those CFCs and all of the related compounds, HFCs, HCFCs, etc., these are all really good greenhouse gases. I mean, really effective greenhouse gases. They have a high global warming potential. I posted a comprehensive list. I don't know if it's complete, but it's a pretty long one onto the Moodle, so you can take a look at these specific CFCs and several other compounds as well. So you can figure out what these guys are. But they're in the like tens of thousands, maybe thousands to tens of thousands global warming potential. So they're pretty significant global warming guys. So, and then of course we have water vapor as well, which we'll kind of talk a little bit more about as well. So these are the major greenhouse gases in terms of abundance and global warming potential as well. But let's talk about the changes to these concentrations, because that's what we're trying to do, right? We're talking about that equation. We've talked about the albedo and how it changes. We've talked about how there's not really anything we can do about the solar constant. But let's talk about what's been happening with these different greenhouse gases since we've been paying attention, right? So changes to greenhouse gas concentrations. So carbon dioxide, of course, is the most popular one that we tend to talk about. And this is coming from burning things, right? You probably have studied the carbon cycle before. And if you haven't, it's maybe worth your time to take a quick look. You can usually find a nice visual that just sort of summarizes it for you. The short version is when we breathe or when we decompose or burn things, we release carbon dioxide into the atmosphere. It gets taken up by plants. It also gets dissolved by the ocean. And there's a few other sources and sinks for the carbon, and then it makes a cycle. So when we burn wood and then we have new trees grow, this is a fairly consistent amount of carbon dioxide that's being released or absorbed, as long as we aren't burning more trees than we're planting. But the big change here has been in the petroleum or fossil fuels. And the use of fossil fuels really started in about the 1750s and has just been increasing since then. And so, of course, we don't have data for measuring carbon dioxide until fairly recently because, of course, people didn't know how to do that. But if we look at the Mauna Loa Observatory they have been tracking the carbon dioxide levels over time since, I think, 1957. And they have a really beautiful illustration of it. I'm going to go and grab it right now. Okay, what you are seeing is the trend in the carbon dioxide levels that's being measured at the Mauna Loa Observatory. And the graph on the right-hand side, this is the graph since 1957, 1958, sorry. And you can see this sort of squiggly red line, and you can see the overall trend is pretty clear. There's no ambiguity about this trend. So when we look at this squiggly line, it's not that this is noise. This is very much not noise. What's happening here is that during this downturn in the amount of carbon dioxide, this is the active growing cycle of the plants near the observatory. And so while they are going through their active growing phase in the spring of their season, then they use up a lot of carbon dioxide very quickly, but then as they go through dormancy and into their winter, then the carbon dioxide levels out and increases locally, and then it goes down again and up and down and down and down. So you're seeing this seasonal trend in the carbon dioxide level, which is such an impressive level of precision of measurement that I just am super impressed by it. Anyhow, the black line is our overall trend, and you can see that we have trended upwards very consistently since these data have been measured. However, you can also see that the slope of this graph, like if we look at this 10-year period from 1960 to 1970, you can figure out what this trend of this graph is, what the slope of this graph is, and then you can look at each of these decades, and you can look at the change in the slope increasing. And it's pretty clear that the slope now is a steeper slope. We have a higher rate of increase than we have down in this initial 10 years of data collection. And so this is a trend that we also need to be aware of, because we know that carbon dioxide is a greenhouse gas, and that this amount of increase in the carbon dioxide is not due to some natural source. This is due to human sources using fossil fuels. So let's flip on back here and summarize a few data points. So with the carbon dioxide, we have an increase. And if you look at those trends, our book says this is about a 0.4% increase per year. So we might do a little bit of calculation there and see if we can calculate what that trend is, because this is going to be reflected in the slope. And that we can see that we have a cycle based on plant growth. And this is the part that makes me really, sit up, which is that it's very clear that if we, again, can plant enough plants, new plants, we can make some inroads into decreasing that carbon dioxide concentration, because it is so clear that during the planting season, these plants are taking up a huge amount of carbon dioxide, and so this is one of our great ways of trying to limit the carbon dioxide concentrations that are present. Okay, so let's talk a little bit about methane as well. Oh, wait, I did want to talk about some sources just in case here's our sources. And we can also talk about that these other sources of carbon dioxide or lack of carbon dioxide uptake are changes in land use. So converting forest land into parking lots, for example, is going to decrease the ability of that land to absorb carbon dioxide. So changes in land use is one of our additional lack of sinks. And then there's a lot of industry that we don't really talk about, right? cement industry is a huge producer of carbon dioxide, and it rarely gets discussed when we're talking about carbon dioxide and society. Instead we talk about driving cars, we talk about planting trees. Those are kind of our two big things, right? And the planting trees relates to this land use, and the cars relates to this burning of the fossil fuels. But there's so many more areas that are much bigger than our individual use of our vehicles that I think it's really important that we not lose track of the big picture producers of the carbon dioxide, which are mostly not individuals. Okay, so methane. This is released during petroleum mining. There's usually some natural gas pockets that are present in any kind of mining that's going on. So if you have the heavier petroleum in there, it also leaks from pipelines, from natural gas pipelines. It's produced by livestock. You've probably heard about cows and flatulence, and this is true. It's also from waste, right? So biological waste, as it decomposes, and that's another source from livestock as well, that we have to deal with, both human waste and animal waste. So you get biological waste that's producing methane, and so any kind of like fermentation or breakdown of, I'll just say decomposition, which happens a lot in swamps and marshes. You also get it in rice fields and other farms where you have flooded the land. So there's a lot of different sources for methane. And this is also increasing. So this is increasing by about 6% per year. And you've also probably heard that it's being released from the Arctic tundra in the permafrost, that the permafrost is no longer permafrosted, that it's thawing and releasing methane. And my guess is that this number may be a bit low because the leaks from the pipelines are not well monitored, and so it's going to be hard to get a good estimate of the amount of methane that's entering the atmosphere. So this also can create a positive feedback loop. I mean, this permafrost melting, right? Because as the permafrost melts or thaws and releases the methane, then this is going to warm the atmosphere more, which is going to melt the permafrost more effectively, and etc. So that's another possible feedback loop. Okay, so ozone we just got finished talking about last week. Well, we didn't finish, but we did talk a lot about ozone last week. And this, in addition to being important for our ozone layer, this is a greenhouse gas. And in the troposphere, down where we live, this is mainly produced during smog events. And it's going to contribute to the smog in polluted areas. And we can look at that smog cycle a little bit more in detail a little bit later. And so if we have higher temperatures in the troposphere, then this could lead to more smog and more ozone in the troposphere. And so you could again have a positive feedback loop here. Here's what I'm going to do. Positive feedback loop. And on the other hand, ozone depletion is going to give us lower stratospheric temperatures. So we have two possible events. We've got the possibility of more warming near the ground if we're producing more ozone, but we're also going to have the possibility of colder stratospheric temperatures, which might in fact increase additional ozone depletion because those cold temperatures are necessary to form those stratospheric, polar stratospheric clouds. All right, so nitrous. This is a normal part of the nitrogen cycle, and it's produced by microbes. In both the soil and the ocean. But it's also affected by agriculture and fertilizers. And those are our two main sources of the increase that we've seen. So we have like pre-1750, we had a pretty consistent about 270 parts per billion, not million, but billion, which are probably coming from proxy data, ice cores and that sort of thing. And then in 2005, we are up to 319 parts per billion. And this may not seem like a very large increase, but if we think about the percent difference here, this is an increase of about 18%. And so, that's not insignificant. It's not just noise. And we're seeing a pretty consistent about 0.3% increase per year. Again, mainly based on agriculture and fertilizer use. And it should be noted that N2O is one of those ozone depleters as well. But it's not part of the Montreal Protocol. The Montreal Protocol focuses on our next class of compounds, which are CFCs and etc. and related, because there's too many of them to include. So we already have a pretty good sense for the CFCs. We know that they were invented during the 20th century. They got really rampant use, and then they've been working on phasing them out. However, it's the related compounds that are not being phased out, right? These ones that are not ozone depleters, the HCFCs, the HFCs, and all of the newer compressed or compressor gases, these are also really potent greenhouse gases, and they have long lifetimes, and they are, increasing in use. I don't have numbers here. But this underlines the importance of making sure that people are recycling refrigerants properly so that the refrigerant gases can be reclaimed and sequestered or turned into something else, just to make sure that we don't release them, all over the place into the atmosphere. Okay, so I also want to talk a little bit about water vapor here, because water vapor is another greenhouse gas, and it's important because it's more abundant than the rest. We said that unlike the others, which are usually in the parts per billion or parts per million, this is between something small and up to about 4%. And 4%, that's huge, right? So it's abundant, it absorbs IR well, and so it's important for us to pay attention to it. Now, I said that it has a short lifetime in the atmosphere, a few days is all, which is why we haven't worried about water vapor too much. But the problem is that we have the potential here for another positive feedback loop, because we know that warmer air holds more water. And so if we make it warmer, we're going to be able to, not gaseous water, or liquid water, but gaseous water. So if we increase the global average temperature, then the warm air is going to be able to hold more water vapor, which is going to warm the air more, which is going to be able to hold more water vapor, etc. I mean, up to a point still, but it's something we need to pay attention to. The other part about water is that you need to remember about the energy, right? If we are going from a liquid to a gas, we said that process of evaporation takes heat. And so this is what's happening when liquid water on the ground evaporates into gas. And this would be from the sun. But then when the gases get up into the atmosphere and condense out as clouds, then we have heat going out into the atmosphere. So this is another source of heat energy. This is another way that water warms the atmosphere, is by adding its heat energy as it condenses. And of course, any gas that does this, that forms little water drop or forms little liquid droplets, is going to add energy into the air. Okay, so all of this turns into a big balance of energy in, energy out. Let's go ahead and look at a little chart here from our book that summarizes these. All right, there's a lot to take in here. This is figure 4.3 from your book, so you can, of course, spend some more time with it a little bit later. So what we're looking at here is we're trying to track the energy in and energy out. So I interpreted this to mean that all of the arrows pointing down, these were additions to the energy of the Earth, and then anything with arrows pointing up was energy that was going out to space. So I added up all of these to try and figure out, how things would balance out. So if you want, you can take some time and do this same tally. The units here are in watts per meter squared, and you end up, of course, with a net positive, as you should. But we also do not have clear information here about whether or not this also relates to. But one of the things that this sort of leads to is that we need to pay more attention to what's happening in the atmosphere, because we do have a lot going on. We've got reflection right over here. We've got the atmosphere emitting energy both out to space and then back toward the Earth. We've got this process of energy being absorbed by liquid that's being turned into gas, and then some of that is being released again as the gases recondense. So let's go and take a little bit more time and talk about aerosols as we sort of conclude this unit, talking about factors that affect the radiative balance in the Earth. So the first thing that I want to make sure is totally clear here with the aerosols is that these are very fine particles of either solid or liquid that are suspended so they don't fall to Earth. So they could be bits of dust, they could be bits of ash from incomplete combustion or forest fires. They can be little bits of even sea salt that have gotten blown up. Of course, volatile organic compounds from lots of different things, smog, these can form droplets. Little bits of water, these guys are all different kinds of droplets. So aerosols generally are a cooling influence. And so for this reason, there's actually been some suggestions that we mitigate the climate change, I will say warming specifically, by injecting sulfur into the atmosphere. They're specifically interested in sulfate. I had to look this one up because I thought, what on earth? I really did. So I needed to know more about the details of this proposal. So they want to get some more sulfate in the atmosphere. And the reason for this, so the idea behind this is that we're coming back to those volcanic eruptions again. Volcanic eruptions contain a lot of sulfur. And they contain sulfur-containing gases like SO2, sulfur dioxide, or dihydrogen sulfide. And we noticed that when we have volcanic eruptions, those cause cooling events. So you remember I already talked about the Tambora eruption. So the idea was, well, maybe if we just inject some sulfate into the atmosphere, then we can mimic the volcanic eruptions and do some cooling, and that will mitigate the climate change that we are seeing and get things under control. So I'd like you to spend some time thinking about this. Do a little bit of research. I'm going to write the details up for our homework 11, so you can check that out onto the Moodle. But even if we just think about sulfur dioxide interacting, for example, maybe with water droplets, or dihydrogen sulfide interacting with water droplets. Ultimately, of course, the idea is that we are going to make H2SO4. But I'd like you to spend some time thinking about not only what are these chemical reactions that are taking place, how are we making this sulfuric acid, that's what this H2SO4 is, and what kind of possible impacts could you imagine even before you do research on what sulfuric acid might be like if we inject this into the stratosphere. So on homework 11, we're going to do a little bit of research on this, on these aerosols. We're going to find out some of the pros and some of the cons and think about some of the chemical reactions that might be taking place here, and then talk about some of the implications that are involved.